Okay. All right. Thanks everyone for joining again during these strange times. So this is lecture 12 of our deep learning course for the spring semester. So a few announcements again. The deadline for the projects is April 27th, Monday, 5 p.m. And the presentations are going to take place on April 30th. Okay, and you can find the details on grading in our GitHub page. So last week we talked about natural language processing and pre-training and applications. Today we will switch gears a little bit and we'll go back to computer vision and we will discuss some advanced topics in computer vision. So today we will introduce image augmentation and fine-tuning methods. And also we will explore some various methods of object detection and also semantic segmentation on images. And finally, we will talk about this really exciting concept called generative adversarial networks. So let's start with image augmentation. We mentioned that the large-scale datasets are prerequisite for the successful application of deep neural networks. And image augmentation actually expands the scale of training datasets by making a series of random changes to the training images to produce similar but different training examples. So another way to explain image augmentation is that randomly changing training examples can reduce a model's dependence on certain memories. So it improves its capability for generalization because it won't be able to memorize images when you show them randomly changed images every time. And actually we can say that image augmentation contributed greatly to the success of AlexNet. So what are the common image augmentation methods? For example, if you have a cat image, you can basically just flip it like this, or you can crop it, or you can change the color, or you can even overlay multiple methods to one image. So let's start with fine tuning. So assume that we want to identify different kinds of chairs in images, okay? And one possible method to do this is to first find 100 common chairs and take 1,000 different images with different angles for each chair and then train a classification model on the collected image data set. But this data set may be larger than FashionMNIST data that we have been working on, but the number of examples is still going to be less than ImageNet until, unless you spend years of taking images to find different chair images. And this may result in the overfitting of the complicated model applicable to ImageNet on this data set. So in order to deal with this problem, an obvious solution is to collect more data, but let's say collecting and labeling data can consume a lot of time and money. So what do? So you are given a task to classify different kinds of chairs and you don't have much data sets. You can actually collect some images, but still it is far from the scale of ImageNet. So here another solution than collecting more images is to apply transfer learning to migrate the knowledge learned from the source data set, which can be ImageNet in this case, to the target data set, which is going to be the chair images. For example, although the images in ImageNet are mostly unrelated to chairs, models trained on this data set can extract more general image features that can help identify edges, textures, shapes, and object compositions. And these similar features may be equally effective or important for recognizing a chair too. So now we are introducing a common technique in transfer learning called fine-tuning. So fine-tuning consists of the following 4 steps. So you first pre-train a neural network model on the source data set. Okay, so for example, this source data set can be ImageNet data set. And then you create another new neural network model which we will call a target model, that replicates all model designs and their parameters on the source model. So this is a source model, this is the target model, and we just copy whatever layers and weights learned from the source model, except on the output layer, because we want to classify images. So what we are outputting, or number of categories for chairs, might be different than the number of categories in ImageNet dataset. And in a third step, we can add this output layer, whose output size is the number of target dataset categories, to the target model. And we randomly initialize this, target model with the parameters. So we randomly initialize the output layer, but we initialize these layers that we copied from the source model using the weights learned from the source model. And now we train the target model on the target data set, of course. And now let's talk about some object detection and also bounding boxes. In image classification tasks, we assume that there is only one main target in the image, and we only focus on how to identify the target category, right? So we have been trying to classify, for example, for fashion analyst data set, we were trying to classify shoes and t-shirts. We never assume that one image might belong to two categories. But in many situations, there are multiple targets in the image that we are interested in. For example, one image can have both shoe and also t-shirt. And we not only want to classify them, but also want to obtain their specific position in the image. So if you have an image and you want to identify shoe and also t-shirt, you also want to identify where they are located in this image. And in computer vision, we refer to such tasks as object detection or object recognition. And it is widely used in many fields. For example, in self-driving cars, we need to plan routes by identifying the locations of vehicles, pedestrians, roads, and obstacles in the captured video image, right? So we need their locations as well. And also systems in the security field needed to detect abnormal targets such as intruders or bombs. So let's talk about the bounding boxes, what we really mean by this. So in object detection, we usually use a bounding box to describe the target location. So for example, in this case, this is a bounding box for dog and this is a bounding box for cat. And the bounding box is a rectangular box that can be determined by the X and Y axis coordinates in the upper left corner, and the X and Y axis coordinates in the lower right corner of the rectangle. So if I want to define this rectangle, I need to use this, the location of this point and also location of this point. So I will have 4 values to represent one rectangle. And the origin of the coordinates in this image is the upper left corner. So this is the origin. So this is where you start is 0 for X and Y. So for example, for this dog image, we will have the values in the axes for this point, which is going to be 60 and 45. And these values are going to be 378 and 516, and similar for the cat box. Okay. And object recognition, the object detection algorithms usually sample a large number of regions in the input image, determine whether these regions contain objects of interest, and adjust the edges of the regions so as to predict the ground truth bounding box of the target more accurately. So different models may use different region sampling methods, but here we introduce a method that generates multiple bounding boxes with different sizes and aspect ratios while centering on each pixel in the image. And these bounding boxes are called anchor boxes. So how do we generate multiple anchor boxes? So assume that the image that you have has a height of H and width of W. And we generate anchor boxes with different shapes centered on each pixel on the image. So let's say we have two parameters here, S and R, and then we generate a anchor box with size WS divided by square root of R and HS divided by square root of R. So here W is the width again, and S is the size, or WS actually becomes the size in the X dimension, and also you normalize it by the aspect ratio. Okay, and when the center position is given, an anchor box with known width and height can be determined. So let's set a set of sizes as S1 to Sn, and also a set of aspect ratios from R1 to Rn. And if we use a combination of all sizes and aspect ratios with each pixel as the center, the input image will have a total of W times H times M times N anchor boxes. So this is of course going to be too many, right? So although these anchor boxes may cover all ground truth bounding boxes, the computation complexity is often excessive. So instead, we are usually only interested in a combination containing S1 or R1 sizes and aspect ratios. So for example, if you are given S1 to Sn and R1 to Rm, so what you will be computing is S1 R1, S1 R2, and so on, S1 Rm, and next it will be S2 R1, S3 R1, and Sn R1. So for example, in this toy example, we have sizes S's 0.75, 0.5, 0.25, and ratios is 1 to 1/2. And here, so S1 R1 is going to be 0.75 and 1. So it is going to be this light green box here. And S1 R2 is going to be 0.75 and 2, which is going to be this pink one, and so on, okay? And then the number of anchor boxes centered on the same pixel is going to be n plus m minus 1. So for the entire input image, we will generate a total of WH, which is the total pixel sizes, times n plus m minus 1. So this is a lot smaller than having n times m. And now the question is how to measure how well the anchor box covers the target. So we measure the similarity between the anchor box and the ground truth bounding box. So for this, let's introduce this metric called Jacquard index, which is defined as for given set A and B, Jacquard index is the size of their intersection divided by the size of their union. So it can be mathematically defined as this. And in our application, we can actually consider the pixel area of bounding box as a collection of pixels, right? So you can consider A is anchor box and B is a ground truth box. And when we measure the similarity of two bounding boxes, actually we don't use this term Jacquard index. Instead, we usually refer it as intersection over union. So, so we will call it IOU. So it will be like intersection between two images and also divided by the union of those two images. Okay. And now the question is how to label training set anchor boxes. So in the training set, we consider each anchor box as a training example. So in order to train the object detection model, we need to mark two types of labels for each anchor box, right? First, the category of the target contained in the anchor box, for example, is it a cat or a dog? And second, the offset of the ground truth bounding box relative to the anchor box. So basically, this is going to be the location. So even if you identify cat image, but where is that really located? So in the training set, each image is labeled with the location of the ground truth bounding box and the category of the target contained. After the anchor boxes are generated, we primarily label anchor boxes based on the location and category information of the ground truth bounding boxes, similar to the anchor boxes. And now you may ask, how do we design ground truth bounding boxes to anchor boxes similar to them? So let's assume we are given anchor boxes as A1 to A and A, and the ground truth bounding boxes are B1 to B and B. So let's say NA is 9, so we have 9 anchor boxes, like here. And then let's say NB is 3, so we have, NB is 4, then we have 4 ground truth bounding boxes. Okay, and of course we want anchor box in this anchor boxes more than the ground truth bounding boxes. So for this, we actually define a matrix X, which is whose size is determined by NA and NB. So in this case, it is going to be 9 by 4. And then for each element in this matrix, each element Xij is going to be the intersection of union of the anchor box AI to the ground truth bounding box Bj. So basically here, each Xij is going to be, for example, X23 is going to be the IOU metric between anchor box 2 and ground truth box 3. And once you identify the largest value of this IOU metric in this matrix, then you actually discard all the columns and, all the rows and also the columns corresponding to that metric. And then you look for the remaining values. And then let's say the next largest value is X71 here. And then we are going to discard this row and this column. And once you do that, we are left with only these blue boxes here. And let's say the largest value of IOU is X54 here. And then we also discard all the corresponding columns and rows. And then what happens? So we actually associated each ground truth bounding box with an anchor index, but we still have some anchor boxes that we didn't really label as any of the ground truth boxes. In that case, for example, let's say which one has never been identified. So we map, so X7 has been mapped, X2 has been mapped, 5 has been mapped. And for example, with the remaining ones, we can actually just look at the for each anchor box that hasn't been mapped to any ground truth box, we can just find the maximum value of the, we can just determine the ground truth boxing that gives the maximum IOU. But if the value is too small, if the value is below some threshold, you just don't label it, or you label it as like background image. Okay, so for example, in this case, let's say we have 2 categories, dog and cat. Dog is classified as 1 and cat is classified as 2. And let's say 0 means background. So we actually start by looking each of the anchor boxes here. And then if we identify, so basically for each bounding box here, we check if they belong to 0, 1, or 2. For example, this blue one, okay? So apparently this is, actually we start with the one that has the highest score. So among all these boxes, so probably this black one has the highest IOU, and also this other black one has another highest IOU. So we actually assign dog and cat to these anchor boxes, okay? And for the remaining ones, we say, okay, so for example, if you look at the red one, it is actually more similar to cat. And if we look at this one, it actually looks more like a background and so on. So for example, in this case, so this box is labeled as 0. So this is labeled as background, and this box is labeled as dog. So it is 1. And this box is labeled as, sorry, 1, yeah, so the red one, 2 is labeled as cat, so we assign 2 to that one. And 3 is labeled as 0, so we assign, labeled as background, so we assign 0 to that. And 4 is labeled as cat, so we assign 2 to that, okay? And the offset of the anchor box is set according to the relative position of the central coordinates of B and A. So basically, instead of using these locations XA, YA, XB, YB, we actually normalize them so that they are all aligned to each other. And during model prediction, we first generate multiple anchor boxes for the image and then predict categories and offsets for these anchor boxes one by one. And then we obtain prediction bounding boxes based on anchor boxes and their predicted offsets. And when there are many anchor boxes, many similar prediction bounding boxes may be output for the same target. And to simplify the results, we can remove similar prediction bounding boxes. And a commonly used method is called non-maximum suppression for this case. Let's see, actually. So here I describe how it works. So for a prediction bounding box B, the model calculates the predicted probability for each category, and assume that the largest predicted category is P, and the category corresponding to this probability is the predicted category of B, okay? And we can also refer to P as the confidence level of the prediction bounding box. And on the same image, we sort the prediction bounding boxes with predicted categories other than background by confidence level from high to low, and obtain a list L. And we select the prediction bounding box B1 with the highest confidence level from L as a baseline, and remove all non-benchmark prediction boxes with an IOU with B greater than a certain threshold from L. At this point, L retains the prediction bounding boxes with the highest confidence level and removes other prediction boxes similar to it. And next, we select the prediction bounding box, let's call B2, with the second highest confidence level from L as a baseline, and then remove all non-benchmark prediction bounding boxes with an IOU with B2 greater than a certain threshold from L. And we repeat this process until all prediction bounding boxes in this list L have been used as a baseline. At this time, the IOU of any pair of prediction bounding box in L is less than the threshold. And finally, output all prediction bounding boxes in the list L. So for example, if you have all these prediction bounding boxes as an output from your algorithm, so we first check the bounding box that has the highest probability. So it looks like dog and cat are pretty much similar. So let's start with dog. So the blue one, okay, so that has highest probability. And then I look at other bounding boxes here that has so much overlap with the blue one, because if blue one has already the highest score, highest probability score, then I don't need similar boxes that actually have the same information. So in this case, for example, the green box and red boxes are actually unnecessary here. So I can get rid of them because they have so much overlap with the blue box. But blue and pink don't have much overlap. So I keep the pink one too. So in my output, I can actually just use these two prediction bounding boxes, okay? So far we generated multiple anchor boxes centered on each pixel of the input image. And these anchor boxes are used to sample different regions of the input image. However, if anchor boxes are generated centered on each pixel of the image, soon there will be too many anchor boxes to compute. And, but it is actually not that difficult to reduce the number of anchor boxes. We can apply uniform sampling on a small portion of pixels from the input image and generate anchor boxes centered on the sample pixels. And also, we can generate anchor boxes of varied numbers and sizes on multiple scales. So let's say, actually, this is based on the observations that smaller objects are more likely to be positioned on the image rather than larger ones. So let's say we have an image of 2 by 2, and let's say there are objects with shapes 1 by 1, 1 by 2, and 2 by 2. So for each of these objects, for the first one, there are 4 possible positions in the image, right? Because it's only 1 by 1 dimensional. But for this one, there are 2 possible positions. But for 2 by 2, there is only 1 possible position on an image. So when using smaller anchor boxes to detect smaller objects, we can sample more regions. And when using larger anchor boxes to detect larger objects, we can sample fewer regions. So here actually it illustrates how we can detect more or less objects by changing the size of the anchor box. So for example, here, since we have smaller anchor boxes, we actually have higher chance to find more of these objects in the image. But if we have a really large anchor boxes, then we have, so that there are less possible positions for these objects in the entire image. You can actually play with the object detection dataset Pikachu if you are interested, and there's an application done in MXNet in our book. And let's talk about single-shot multi-box detection. So now we will use our knowledge on bounding boxes and anchor boxes and multi-scale object detection to construct an object detection model, which is called single-shot multi-box detection. This model is widely used, and some of the design concepts and implementation details of this model are also applicable to other object detection models. So the Bayes network is used to extract features of original images. So the closer a feature block is to the top, the better suited it is to detect larger objects. So as the SSD, single-shot multi-box detection, generates different numbers of anchor boxes of different sizes based on the Bayes network block, and also each multi-scale feature block, and then predicts the categories and offsets of the anchor boxes in order to detect objects of different sizes. So SSD is actually a multi-scale object detection model. So we are actually extracting anchor boxes both from the initial phase of the neural network, and then we go deeper. As we go deeper, so we can actually extract multi-scale features. And region-based SNNs or RSNNs, this is a model that first selects several proposed regions from an image. For example, anchor boxes are one of the selection methods, and then label their categories and bounding boxes or offsets. Then they use CNN to perform forward computation to extract features from each proposed area. And afterwards, we use those features of each proposed region to predict their categories and bounding boxes. So specifically, our CNNs are composed of 3 main parts. First, selective search is performed on the input image to select multiple high-quality proposed regions. The category and ground truth bounding box of each proposed region is labeled. And second, a pre-trained CNN is selected and placed in truncated form, so before the output layer, and it transforms each proposed region into the input dimensions required by the network and uses forward computation to output the features extracted from the proposed regions. And third, the features and labeled category of each proposed region are combined as an example to train multiple support vector machines for object classification. But the main downside of RCNN is the slow speed. The main performance bottleneck of an RCNN is the need to independently extract features for each proposed region. As these regions have high degree of overlap, independent feature extraction results in a high volume of repetitive computations. So fast RCNN improves on the RCNN by only performing CNN forward computation on the image as a whole. So its primary computation steps can be described as below. So compared to an RCNN model, a fast RCNN model uses the entire image as the CNN input for feature extraction rather than each proposed region. Okay, so that's the main difference. And second, assuming selective search generates n proposed regions, their different shapes indicate regions of interest of different shapes on the CNN output. And third, fast RCNN introduces ROI, which means a region of interest pooling, which uses the CNN output, and the ROIs is input to output a concatenation of the features extracted from each proposed region. And finally, there's a fully connected layer, and then we can finally determine the offset and also category of the image. So there's also faster RCNN. So fast RCNN generally requires that many proposed regions be generated in selective search, but faster RCNN replaces selective search with a region proposed network. So it changes this, this part in the architecture, and this reduces the number of proposed regions generated while ensuring precise object detection. So far, we only used rectangular bounding boxes to label and predict objects in images. Now we will look at semantic segmentation, which attempts to segment images into regions with different semantic categories. For example, in this case, we can actually label each pixel here if it is a dog image or if it's a cat image. And now we need to introduce this concept of transpose convolution. So the layers we introduced so far for convolutional neural networks, including convolutional layers and pooling layers, often reduce the input width and height or keep them unchanged. And applications such as semantic segmentation and also generative adversarial networks require to predict values for each pixel and therefore needs to increase input width and height. So transpose convolution, also named fractionally strided convolution or deconvolution, serves this purpose. So let's consider a basic case where both input and output channels are 1 and padding is 0 and stride is 1. And this figure illustrates how transpose convolution with a 2x2 kernel is computed on 2x2 input image. So for example, if this is my image and this is the kernel, I first multiply this pixel 0 with kernel, and then so 0 times 0 is 0, 0 times 1 is 0, 0 times 2 is 0, 0 times 3 is 0. And I do that, I do the same thing for this pixel here too. So which is going to be 1 times 0, 0, 1 times 1, 1, 1 times 2, 2, and 1 times 3, 3, and so on. And finally, for the output, we sum up all of this. So as you see, we actually increase the image size. And semantic segmentation uses each pixel in an image for category prediction. Fully convolutional networks use convolutional neural network to transform image pixels to image categories. So an FCN transforms the height and width of the intermediate layer feature map back to the size of input image through transposed convolution layer. And this way the prediction have a one-to-one correspondence with input image and spatial dimension. So fully convolutional network first uses the convolutional neural networks to extract image features, then transforms the number of channels into the number of categories through one-by-one convolutional layer, and finally transforms the height and width of the feature map to the size of the input image by using the transposed convolutional layer. And the model output has the same height and width as the input image and has a one-to-one correspondence in spatial positions. And the final output channel contains the category prediction of the pixel of the corresponding spatial positions. Okay, so this was all about object detection and also segmentation. So now let's introduce this really interesting and exciting concept called generative adversarial networks. So throughout this course, we talked about how to make predictions. In some form or another, we use deep neural networks, learned mappings from data points to labels. This kind of learning is called discriminative learning. So we'd like to be able to discriminate between photos of cats and photos of dogs. And classifiers and regressors are both examples of discriminative learning. But there is more to machine learning than just solving discriminative tasks. For example, given a large data set without any labels, we might want to learn a model that concisely captures the characteristics of this data. Given such a model, we could sample synthetic data points that resemble the distribution of the training data. This kind of learning is called generative modeling. In 2014, a breakthrough paper introduced generative adversarial networks, which is a clever way to leverage the power of discriminative models to get good generative models. At their heart, GANs rely on the idea that a data generator is good if we cannot tell fake data apart from real data. So in statistics, this is called a two-sample test, a test to answer the question whether the data sets X and X prime were drawn from the same distribution. And the main difference between most statistics papers and GANs is that GANs use this idea in a more constructive way. So in other words, rather than just training a model to say, hey, these two data sets don't look like they came from the same distribution, they use the two-sample test to provide training signal to generate a model. So this allows us to improve the data generator until it generates something that resembles the real data. So at the very least, it needs to fool the classifiers. So there are two pieces to GANs, the generator network and the discriminator network, which attempts to distinguish fake and real data from each other. And both networks are in competition with each other. And the generator network attempts to fool the discriminator network. And at that point, discriminator network adapts to the new fake data. So this information in turn is used to improve the generator network and so on. And the discriminator is a binary classifier to distinguish if the input X is real, in other words, it's from real data, or fake, in other words, from the generator. And let's assume the label Y for true label is true data is 1 and 0 for fake data. Then the loss function for this discriminator is going to be the cross entropy loss, which can be defined as this. So d of x, you want d of x to be 1 if y is from a true data, but you want d of x to be 0 if y is from a fake data. And discriminator tries to minimize this cross entropy loss. And for the generator, it first draws some parameter z from a source of randomness, and we often call z the latent variable. It then applies a function, let's call it g, to generate x prime. So here, given this noise and passing it through this generator, which is a neural network, and also let's call it g, and then output is going to be g of z, and let's call it x prime. And the goal of the generator is to fool the discriminator to classify x prime as true data. So your generator wants to tell discriminator, hey, my data is actually not fake, it is real. Of course it is not, and discriminator tries to be like, no, you cannot fool me, and this way they will be competing with each other. So in other words, we update the parameters of the generator to maximize the cross entropy loss when y is 0. So we want to maximize this, and so because the gradients can be too small when we use this loss function, we actually commonly optimize max of log of d of x prime. Okay, so basically we want not we, but the generator wants discriminator to assign 1 when it is given x prime, which is the fake data, as an input. And yeah, so this is just the beginning of the story of GANs, and you are currently at the second red here. And so there is actually a lot more. So there is a conditional GAN in that which you will use if your training data set includes both cats and dogs, let's say. Your GAN will produce blurry half-breeds, and conditional GAN aims to solve this issue by telling the generator to generate images of only one particular class, like a cat, dog, or Nicolas Cage. Or cycle GAN can be used to generate some stylistic images. For example, here, when we are given input, we can actually represent it as like Monet, Van Gogh, and so on. And pro-GANs are progressive growing of GANs. So they actually claim that they can improve, they can improve the stability of training GANs by incrementally increasing the resolution of the generated image. You can read the paper if you are interested in. And also Wasserstein generative adversarial networks suggest that instead of minimizing Jensen-Shannon divergence, which is actually equivalent to KL divergence plus reverse KL divergence, we should be minimizing the Wasserstein distance instead, because it has better properties in terms of gradient. So that was all I wanted to say today. Do you have any questions? Okay, so next week we will continue with unsupervised learning, and we may need to revisit GANs again. Okay, thank you so much and stay safe.